Yesterday when we went through the Millikan oil drop experiment, we made the top plate positive and the bottom plate negative. Today we're going to reverse that. Today we're going to make the top plate negative and the bottom plate positive. I want you to see as we go through our review here that it doesn't matter. Things will look a tiny little bit different, but the basic thought process that we go through will be exactly the same today as it was yesterday. You guys remember how this went, right? You get these two charged plates, you inject these tiny little oil droplets in between these plates, these atomized oil droplets, these droplets that are really, really, really small, and they're charged. Some of them are charged positively, and some of them are charged negatively. Each of those two oil droplets, the positive ones and the negative ones, will experience two forces. The force of gravity, which acts down on a positive drop and downward on a negative drop. Gravity isn't affected by charge. Gravity is affected by mass. And since both of these oil droplets have mass, and the force of gravity is down on anything with mass, gravity will be down on both of these. But there's also an electric force. Can you tell me, please, which direction the electric force would act on the positively charged oil drop? Does the electric force pull it down as well, or does it push it up toward the top? Doesn't matter. Okay, we're not asking the question, is it suspended or traveling at a constant speed, or is it accelerating? Look at the scenario that we have right here. We have a negative plate at the top, we have a positive plate at the bottom, we have a positive charge right there. I'm not asking which way it's going to go, whether it's going to accelerate or be suspended. I'm asking which way is the electric force acting on it. It's going to be up. Thank you. It's going to be upwards toward the negative plate. Right? It's in the direction of the field, which is from positive to negative. Now, what about the other one? What about the negative charged oil droplet? Which way is the electric force going to be on it? Logically, it's going to be downward, right? That's opposite to yesterday. Yesterday it was negative charged particle, we had an electric force acting up. Positively charged particle, we had an electric force acting down. Why is it different today? Because we reversed the polarity of the plates. The top plate was positive, now it's negative. Okay, the bottom plate was negative, now it's positive. We want to take a look at, well, both scenarios, but first we want to take a look at this scenario. In fact, a very special case of that scenario. These two forces oppose each other. Now, that doesn't mean that they're the exact same values. One might be bigger than the other, and if it is, then it's going to accelerate either up or down. But if it's not, then it's going to either travel at a constant speed or it's going to be suspended. Let's take a look at this particle when these two forces balance. Fe equals Fg for those particles that are suspended or traveling at a constant speed. Q times E is my electric force, and M times G is my gravitational force. Q ends up being equal to mg over E. So for those particles, again, that are suspended or traveling at a constant speed, we can find the charge simply by setting those two forces equal to each other, rearranging it, solving for Q. The charge of this oil droplet will be what? Well, it could be 1.6 times 10 to the minus 19. Or it could be 3 times that. Or it could be 6,194 times that. Or it could be 314 times that. It can't be 2.5 times that. Millikan concluded from this experiment that we have to have an elementary charge, the smallest possible charge, 1.6 times 10 to the minus 19, or a whole number multiple of that. We can have an elementary charge, and charge is quantized. One fundamental charge or a multiple of that. Now, if we look at the other particle, the negative particle that is clearly accelerating downwards here, or for that matter, if we look at this one, when these forces don't balance, one force is bigger than the other, we're going to perform our analysis in a slightly different way, but we're going to get the same results here. In this case, we'd say F net is equal to the sum of the forces. F FE plus FG. M times A is equal to QE plus mg. We rearrange and solve for Q. We're once again going to get 1.6 times 10 to the minus 19, or 3 times that, or 6,194 times that, or any whole number multiple of 1.6 times 10 to the minus 19. So same result, slightly different way of obtaining that result. Suspended or traveling at a constant speed versus accelerating either up or down. We had 2 questions for homework last night on that last little bit that we reviewed here. I'd like to do both of these questions, please, on 764. Those answers, remember, were wrong in the book. I think we gave you the correct answers yesterday, didn't we? First one was 2.8 times 10 to the negative 13 newtons. Second one was 5.8 meters per second squared. How many people got those? Anybody get both of those? Anybody get the answers that were in the book already? Yes? Okay, so you made a silly little mistake, a small little mistake, the same mistake as the people that wrote this textbook made. I'll show you what it is in just a second here. The net force on a sphere that has a charge of minus 5e. There's the big thing right there. It's minus 5 times the elementary charge. Let's write that down as our charge. This is our mass. This is our electric field. We want to find the net force. The net force is equal to the sum of the forces. That's Fe plus Fg. We're not going to bother putting in m times a for that because we're not looking for the value of a. We're just looking for the net force. Fe is going to be q times E, q times the electric field, plus m times g. Q is 5 times 1.6 times 10 to the minus 19. Never plug in the sign of a charge, right? It's negative 5, but don't worry about that right now. Okay, it's just 5 times the elementary charge. Multiply that by the electric field. We add that to the mass times gravity. And now we got to worry about signs, positives and negatives. Gravity is always going to be a negative sign because it's acting downward, and it always is. Well, what about the electric force here? Now that we got 1.2 times 10 to the negative 13, as did probably some of the rest of you, get that value. Because you looked at this, I think, and said, oh, electricity is upwards. Gravity is down. Electricity is up. Let's make gravity a negative value. Let's make electricity a positive value. The problem is this. It's a negative particle. A negative particle experiences a force opposite to the direction of the electric field. If the electric field is up, then the electric force on the negative particle will be down. Both of these forces become negative values. And when we consider that, and then we add them together, we end up getting negative 2.8 times 10 to the negative 13, or 2.8 downwards. Is that your mistake, Natalie? You're in good company, right? People that wrote the textbook made the same mistakes. So. Number 2. Here we want to find the acceleration of the sphere if the direction of the field is reversed. So instead of having a field upwards this time, now we got a field downwards. We're going to start off the same way, though. Fnet is equal to Fe plus Fg. But this time we're going to replace Fnet with m times a because we're looking for the acceleration. The mass we have is still 2.0 times 10 to the negative 14. And we're solving for a. Let's go back and worry about the signs now. Gravity will be down again. So it's going to be negative again. The electric force will be, well, this time the field is downward. and the force is going to always be opposite to the field since it's a negative particle, the force is going to be upward this time. It's going to be a positive value. When we sub in those positives and negatives, we end up getting an acceleration of 5.8 meters, negative 5.8 meters per second squared, which means 5.8 downward. Justine, is that okay? Just looked like you had a bit of a puzzled face there for a sec. It's good? Yep. Well, that's a good question. It can come from two ways. There's friction taking place between the nozzle and the oil droplets, and anytime you have friction between two things, you're going to get charge transfer. So you can get some charge built up on these things, on these oil droplets by the by the friction. And we don't usually talk about this in Physics 30, but since you asked the question, I will. The other thing that he actually did was irradiate it with X-rays. When he irradiated it with X-rays, X-rays is what we call ionizing radiation. That turns particles, atoms, or things that are not charged into ions or things that are charged. So if you irradiate these oil droplets with X-rays, they become charged as a result of that. So theoretically, you might get some charged enough to do this experiment without irradiating with X-rays because of friction. But in the absence of having enough charge on those oil droplets, we've got the backup plan, which is the X-rays. Again, I didn't talk about that with you guys because that's not the main part of this. The main part of this is the discovery of the charge of the electron. But it's a good question. Oh, is that right? Oh, is that right? Did you guys learn about the oil drop experiment or the AP? Oh, it's too bad. It's too bad that you hadn't done this a couple weeks before, right? I'm going to give you a few minutes to work on these questions on 767, questions 1 to 7. Okay. See what you can do, and we'll give you 5-10 minutes, and then we'll go back at our new stuff for the day. Today our new topic is going to be radioactivity. To do radioactivity, which is a process that we'll describe in just a few moments, we have to first introduce the idea of what we call isotope notation. Those of you who have taken chemistry or are taking chemistry will know full well what an isotope is. It's a version of an element. Same number of protons, different number of neutrons. Carbon, for instance, has 6 protons. There are different versions of carbon, though. There's carbon-12, there's carbon-13, there's carbon-14. 6 protons for all 3 of those. One of them has 6 neutrons, one of them has 7 neutrons, one of them has 8 neutrons. Isotope notation describes the properties of a particular isotope for us. How many protons it has and how many neutrons it has. The notation would look something like this, where X represents the chemical symbol. For carbon, it would be C. For iron, it would be Fe. For uranium, it would be U. Z represents the atomic number. The atomic number is the number of protons. So you can always tell how many protons a particular atom has by looking at its atomic number. A, on the other hand, the number in the top left-hand corner, will stand for the mass number. The mass number is the number of protons, again, but this time it's the number of protons and the number of neutrons together. This is important for us not as an end in itself. We don't usually have to look at isotope notation and answer a question how many protons, how many neutrons something has, although it does happen from time to time. For the most part, we have to recognize isotope notation because we use it as a tool for the topic we're about to do, radioactivity, and then the topic after that, fission and fusion. Sometimes we need to know when we're talking about radioactivity how many protons or how many neutrons something has, and we determine that by using this isotope notation. Gold 197 has a mass number of 197 and an atomic number of 79. We're asked to find out how many neutrons gold-197 has. But first, let's get the number of protons. This is easy. How many protons does gold-197 have? 79. Yeah, it's the atomic number. How many neutrons does it have? Well, the number of neutrons is a little bit tougher. We're going to take that 197, the number of protons and neutrons combined, and we're going to subtract from that 79, and we're going to get 118. We get 118 neutrons in this particular isotope of gold. Now, the normal way of writing isotope notation looks like this, but we can also see a bit of a shortened form of it. If we're not given the atomic number here, how are we possibly going to figure out the number of neutrons from this? If you saw that on a test, what would you do? Check your periodic table. Right? You've got a periodic table at the end of your data booklet. The only reason you will use your periodic table in Physics 30 is to get the atomic number of elements, the number of protons. So we can look that up, and we find that although the mass number changes for gold depending upon which isotope it is, the atomic number is always 79. You may also see it written like this. If you see any of those, not 79, 197. If you see any of those, it means exactly the same thing as the question that was given to us. They're just taking a bit of a shortened way of doing it. Go ahead. 118. The answer was 118 neutrons. We took the number of protons and neutrons combined and subtracted the number of protons, gave us a number of neutrons. Good? I will give you 63 seconds to answer these two questions, please. Today we talk about radioactivity. The tool that we just learned, this isotope notation, will allow us to understand radioactivity a little bit more, the particles that are given off, what's left over after radioactivity has occurred. Radioactivity is a natural process. It's a spontaneous process. That means it happens on its own. We don't control it. It happens on its own when it wants to happen. Somebody gets poisoned with a radioactive polonium-210, let's say. The person that poisoned them can't control how quickly that kills the person. It can't control how quickly that radioactive material, polonium-210, will decay. We know statistically it will decay this quickly, just based on past performance. And in all likelihood, if we have a big enough sample size, it will continue that pattern. But we don't control it. It's a spontaneous process, it's a natural process, it's a random process in which one nucleus of one particular atom changes into something else. It decays into something else. And in the process of decaying into another nucleus, it gives off something, it produces something else, like an alpha particle, okay, like the type of radiation that's given off of polonium-210. What comes out of it, not the nucleus that it's turned into, but the thing like the alpha particle, the thing that's produced as kind of a byproduct, we call that ionizing radiation. That means that it ionizes atoms. That means that it turns atoms into charged particles, which means we get chemical reactions taking place that aren't supposed to take place. That's not good when it's inside our bodies. Chemical reactions taking place that aren't supposed to take place lead to cancer in the long term, but they can lead to a whole bunch of other things in the short term, like hair loss, like fingernail loss, like issues with your eyes, like organ failure, like bleeding. None of that stuff is good. Try to avoid it all. There are three types of radioactive decay that we will talk about in Physics 30. Alpha decay, beta decay, and gamma decay. When alpha decay occurs, we have one big nucleus that gets changed into one other, still pretty big nucleus, but slightly smaller. And we also have a part that breaks off. The part that breaks off will have an isotope notation that looks like this, 4,2 alpha. It means it's got 2 protons, it's got 2 neutrons, 2 plus 2 is 4, and it's got no electrons. It's just a couple protons and a couple neutrons. We sometimes write that like this, 4,2 He. What does He stand for? Helium. An alpha particle is a helium nucleus. It's indistinguishable. It's got 2 protons and 2 neutrons. So how does an alpha particle, or a bunch of alpha particles, a bunch of helium nucleuses, kill somebody in 22 days when we breathe helium in, from the birthday balloon to talk with a really high pitch, and it doesn't seem to hurt us? The difference is this. The helium that you breathe in from the balloon are helium atoms. This is a helium nucleus. This is charged. There's a charge of +2. That's a big deal. That makes a big difference. That's ionizing. Helium atoms aren't. Helium nuclei are. There's 2 types of beta decay that we're going to talk about. One's called beta minus. One's called beta plus. You can see that a beta minus particle has no protons and it has no neutrons. But it does have a -1 down there. That -1 means that it's an electron. So sometimes we write it like this instead of 0 minus 1 beta. That begs a question, I think. If the nucleus consists of protons and neutrons, how can you get an electron ejected from the nucleus? Where does it come from? It comes from the nucleus. But there are no electrons in the nucleus. Yeah, I know, but we still get an electron from the nucleus. Doesn't seem to make any sense. We'll talk about that in a minute as well. There's no protons in that either. 0 protons, 0 neutrons. So what's this +1? Well, it's not an electron. That's what we call, Christine? A positron. It's the antiparticle of an electron. It's antimatter. How many people have ever seen Angels and Demons? The antimatter, when matter and antimatter come together, they annihilate each other, they produce pure energy. This is antimatter. This is matter. This is antimatter, the antiparticle of an electron. Antimatter has the same properties as matter except for one thing. A positron is identical to an electron except for its charge. It's positively charged. It has the same mass. It's not a proton because it has the mass of an electron, but it's positively charged. Gamma decay. 0 protons, 0 neutrons, 0 electrons, 0 positrons. Gamma radiation is just electromagnetic radiation. In our last unit, we talked about visible light as being produced from transitions of electrons in the atom, microwaves by oscillating electric charge. We talked about gamma rays being produced by nuclear decay. Today we're going to talk about that. How do these come about? Well, an alpha particle typically comes from a big nucleus. With too many protons. Why is this nucleus not stable if it has too many protons? Well, let's take a look at 2 forces that exist within the nucleus. There's the electrostatic force, which is a repulsive force, right? It can be attractive as well, but between protons, it's going to be repulsive. Proton repels proton. It tries to act to push the nucleus apart, to break the nucleus apart. But there's also an attractive force in there called the strong nuclear force. That pulls the nucleus together. Now, if the strong nuclear attractive force wins, the nucleus is stable. If the repulsive electrostatic force wins, then the nucleus is unstable. If you have too many protons, too many positives, which contribute to the repulsive electrostatic force, then the nucleus breaks apart. When it breaks apart, it gives off an alpha particle. The alpha particle gets kicked out. And then, of course, you're left with a smaller parent nucleus, or daughter nucleus, I should say. Beta decay occurs, and this is the wacky one, because this is the electron that comes out of a nucleus. It doesn't have any electron in it. It's kind of like, you know, David Copperfield pulls a rabbit out of a hat, and there was no rabbit in the hat to begin with. How do you get an electron out of a nucleus when there's no electrons in the nucleus? Well, this occurs when you have too many neutrons. You get too many neutrons in the club. It's the nucleus club. Who belongs in the nucleus club? Well, the protons and the neutrons. But the guys in the club get together and say, you know what, I think we got too many neutrons. We got to get rid of a neutron. One of the guys comes up with a really good idea. We don't want to kick any neutrons out. Let's change a neutron. Let's change them into a proton. And then we've got one less neutron and one more proton. It's perfect, right? We change a neutron into a proton. And then the other guy says, no, we can't do that, because that would violate the law of conservation of charge. We started with something that was neutral. Now we've got something that's positive. We can't do that. So the other guy says, well, let's make an electron as well. Neutral becomes positive and negative, which is neutral. Well, the other guy says, no, we can't do that, because electrons don't belong in the club. We don't have any electrons in the club. And the other guy says, well, let's kick them out. Let's change a neutron into a proton, because we got too many neutrons and not enough protons. But we got to make an electron in the process as well. What do we do with that electron? Get rid of it, because it's not a part of the club. So we end up with, in beta decay, a nucleus that has one more proton than it started with, one less neutron than it started with. We also make an electron that leaves the nucleus. That electron that leaves the nucleus is the beta particle. Positron emission, or beta plus decay, occurs once again when we have too many protons. But this time we're not going to take two protons and two neutrons and kick them out. We're going to change a proton. Too many protons, not enough neutrons? Let's change a proton to a neutron. Guy says we can't do that. Violates the law of conservation of charge. We need something else that's positive to keep the law of conservation of charge. Okay. The other guy says, let's make a positron as well. The electron and the positron can't stay in the nucleus. They don't belong there. They get kicked out. That's the beta minus and beta plus particle. The neutron that's been changed into a proton, it's all good. Protons belong there. The proton that's been changed into a neutron, that's all good, because neutrons belong there as well. Finally, gamma decay. Gamma is electromagnetic radiation. It's different than the rest of these because it's not a particle like that. It's a photon, so it's a particle, but it's not a particle with mass. It's just electromagnetic radiation. It occurs as a byproduct of something else already occurring.
Good afternoon.
Let's say beta decay has occurred. The nucleus is left in an excited state. It doesn't want to be there, though. So it goes back down to its normal state. As it does that, it gives off energy. It gives off electromagnetic radiation. It gives off a photon of gamma ray. So beta decay's occurred. Look at it, guys. You got a neutron that's changed into a proton and an electron. If you saw that, you'd be excited too. The nucleus is excited. It's left in an excited energy state, but it can't stay there. So it goes back and gives off a photon and gives off a gamma ray. So these are a little bit more fundamental. They happen because of a condition that exists in the nucleus, that pre-exists in the nucleus. This occurs as a byproduct of something else, because something else has already occurred and the nucleus is left a little bit excited. That's it for today, guys.